First and second derivatives. When we have a function, we can take its derivative. When you take the derivative, you get a new function, which means you can take its derivative. So if we are looking at a function, we can take the derivative several times. The way you can tell how many derivatives you can take is you note the power. For example, look right here. This is t to the first. That means that you can take the first derivative and you'll still get a function. But after that, if you go to take a second, third, fourth, fifth derivative, you'll just have 0. Look at this one. This one has a power of 2. That means that you can take the derivative twice. You can take the second derivative, and then after that, it will start turning into 0. Let me show you what I mean. Let's look at this together. So if we are trying to find the derivative for this one, we know that our formula for the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. So we need to figure out our different pieces. So let's figure out one thing at a time. In this case, it's g and it's t, but it's okay. It's the same formula. It's the same idea. So we need to figure out g of let's write that a little bit better. G of t plus h. So that's going to look like 3 times t plus h plus 5. So if we distribute that through, that will look like 3t plus 3h plus 5. And then we have to figure out g of t. G of t in this case will be 3t plus 5. It's just our normal function. So now we need to subtract these. Putting them into our formula, we would have our g of t plus h minus g of t all over h. So g of t plus h, that's this one. So that looks like the limit as h approaches 0 of 3t plus 3h plus 5 minus, and this will be all over h. So we have g of t. G of t is right here. Be careful, you're subtracting. Put it in parentheses so that you do not lose your subtraction sign from the front, because you need to be able to distribute that negative. So it'll look like 3t plus 3h plus 5 minus 3t minus 5. Remember, anything that doesn't have an h has to cancel. So let's check it. No h and it cancels right here. 3h are okay. No h, it cancels right here. So now we're left with the limit as h approaches 0 of 3h over h. H over h is 1. So when we go to evaluate, we put the 0 when we don't have any h's left. So it's okay. So the limit is just 3. There we go. So this would be the first derivative. So this means that f, well, let me do it right. Let me put the g. There we go, because it's a function named g. See? So g prime of t equals 3. Now, what if we wanted to take the second derivative? Because it asked us for the first and the second derivative. Well, the problem is that we have a constant. So if we were to try to go back and put this into our formula, if we were to try to go back and find g of t plus h for 3, well, the problem is we're just going to have 3. Because there's nowhere to put the t into. There's nowhere to put another t plus h. There's no parenthesis here, so we don't have anywhere to fill in our different values. And then if we were to find just g of t, we would get 3 again, because there's nowhere to put the t. If we look at this one, there's nowhere to put that variable. So in the numerator right here, when we go to put in our g of t plus h, we'd have 3 minus 3. Which is going to give us 0. And we're not able to do that one. So 0 is going to be the derivative. So what happens, preview, what happens is if you have a constant, the derivative of a constant is 0. So the second derivative here, the derivative of a constant, so in this case, the derivative of 3 is 0. And the reason is we don't have anywhere to put the t's, we don't have anywhere to put the h's, we don't have anywhere to put a variable because all we have is 3. So our first derivative gives us 3, our second derivative gives us 0. And this is what I was saying. If you look at the power here, we have t to the first. So we can take the derivative one time, and then after that, it's going to give us 0. All right, let's look at the second one. So for part B, same idea. We are looking for, this one's f this time, so we're looking for the limit as h approaches 0 of f of x plus h minus f of x all over h. So we need to figure out our pieces. We need to find our different parts. So the first thing we need is f of x plus h. So that will look like 1.5 times x plus h quantity squared minus 1.5. There we go. We're substituting in our x plus h. There we go, plus 3.7. All right, let's clean this up. So if we have x plus h to the second, let's do that up here where we have some space. X plus h quantity squared. That means x plus h times x plus h. So if we FOIL that through, we'll get x squared plus, so x times x is x squared, x times h times x, so that's 2xh. H times h is h squared. So I still have a 1.5 in front of that. So we need to distribute our 1.5 to this right here. And that's going to look like, leave myself a little bit more space this time. 1.5 x squared. 1.5 times 2 is going to give us 3x plus h. No plus, it's just 3xh. Because it was 1.5 times 2 is 3, and then xh. Plus 1.5 h squared. Distribute your minus. Minus x minus h plus 3.7. That's the first piece. Let's try the second piece. So the second piece is f of x. So f of x will look like 1.5 x squared minus x plus 3.7. Okay, we got it. Let's see if we can substitute it all in. So we have our different pieces here. We have our f of x plus h, we have our f of x, and we're going to put it all over h. So let's do some highlighting so we can color code. Here is our f of x plus h. So that goes right here. So we have the limit as h approaches 0 of 1.5x squared plus 3xh plus 1.5h squared minus x minus h plus 3.7 minus, now don't forget to distribute your negative to all of this. So minus 1.5x squared, I'm out of space, I'm just going to have to start a second row, plus x minus 3.7. All over h. All right, let's start doing some canceling. Remember, anything that does not have an h has got to cancel. So let's see what all we can get rid of. Here is a 1.5x squared minus 1.5x squared. That helped a little bit. 3xh has an h, 1.5h squared has an h, minus x plus x. Minus h has an h, plus 3.7 minus 3.7. Let's rewrite this so that we can see what we're working with. So we have the limit as h approaches 0 of 3xh plus 1.5h squared minus h. Did I get everything? Everything has an h. We're okay. So this, we need to pull an h out. So we have the limit as h approaches 0 of h times 3x plus 1.5h. And then when you factor an h out of the minus h right here, it just becomes minus 1 all over h. H over H cancels. And now we're going to take our 0 and we're going to substitute it in where we had our H before. So that goes right there. So that will leave us with no limit anymore. You don't write the limit because we are substituting in. So 3x plus 1.5 times 0 minus 1. So that means that our first derivative is going to be 3x minus 1. Now we need our second derivative. And so if we need our second derivative, that means we would go through this whole process again. I want you to notice something. Look at this one right here, 3x minus 1. Look at this one over here, 3t plus 5. Solving our second derivative here is very similar to what we did here, so I'm going to let you try it out. I'll give you a heads up. Our second derivative works out to be 3. Give it a try. Make sure you can get 3. It will look just like what we did in part A as you solve it down through, only you have an x now instead of a t. Let's look at the next piece. The graph of the derivative f prime of a function f is shown. On what intervals is f increasing or decreasing? So this is looking at the derivative, looking at the increase and looking at the decrease in terms of the slope of the tangent line. So when we look at this, it says the graph of the derivative is shown. Look right here. That means that this blue line here, this is the derivative graph, not the original function. This is the derivative. So remember, if the derivative is positive, then the function was increasing. So looking at the graph of the derivative, anywhere that the graph is above the x-axis, then that means the original graph was increasing because the derivative is positive. So these two pieces right here is where the original graph was increasing. So what are those? So let's see here, increase. That looks like we're looking at from 0 to x being 1. So we're just going to write an interval. So we're going to write 0 to 1. These are the x values. And increasing, it looks like from 3 to 5. This is an interval. It is not a point. It's not the 0.35 x and y. It is an interval. These are x's, and between these x's, we are increasing. So then if we look like the decrease piece, then that means that we're looking for where it is below the x-axis. If the original function was decreasing, then that means the derivative will be negative, which means the derivative will be less than 0, which means it will be below the x-axis. So that will be from 1 to 3 for this first interval. And it looks like we have 5 to 6 for our second interval. On what values of x does f have a local max or a local min? A max or a min? A max or a min means that we are going to have a derivative value of 0. So that's where it's going to touch the x-axis. So that means that we have a max or a min at 1, 3, and 5 in this case. How can we tell which is which? Well, let's see if we can figure that out. We need to figure out which ones are a max and which ones are a min. So let's think about it here. Our graph was increasing on this interval. And then it changed to decreasing on this interval. So if it was increasing and then changed to decreasing, so it was increasing, it was going up, and then it changed to decreasing, that would give us a max. So at 1, right here, we're going to have a max. Now we don't know the y-coordinate because we don't know the function, so we can't figure that out, but we know that it's going to be a max at 1. Let's check the next one at 3. So at 3, we were decreasing, so we were going down, we were decreasing, and then changed to increasing. So that's going to give us a min. So at x equals 3, we would have a min. Let's try the last one, x equals 5. It was increasing, it was above the x-axis, it changed to decreasing. That's going to give us another max. Whoops, I forgot the end. Let's try that again. So at x equals 1 and x equals 5, we have a maximum. And at x equals 3, we have a minimum. If it is known that f of 0 equals 0, sketch a possible, notice it says possible. We don't have the y scale, so we're just doing the best that we can. Sketch a possible graph of f. So what could this look like? Well, let's see if we can get a guesstimate of what it could look like. Let me get rid of this piece right here so we have a little bit more space. So we know that f of 0 is 0. So that's giving us a starting point right here. And then we know that we were increasing until right here. So let's put a dot right there. So it was increasing, meaning it was going up. There we go. Then we know we were decreasing until here. So let's decrease. Now we don't know if it crossed the axis. It could have just decreased very gradually and just been all up in this first quadrant. We don't know. That's why it says a possible. So I'm going to make mine more drawn out so that I have a bigger possible graph. But we're just drawing a possibility. We're guessing the best that we could. Then it is showing us that we were increasing again until we get to here. So I'm going to switch over to increasing again. There we go. And then we were decreasing to finish it off. Now there's some things that we do know that I drew in here that we haven't talked about yet, and I'll give you a little bit of a preview of those. When we are talking about our functions, you see right here where we have a maximum on our derivative, that's going to be a 0 for the function. It'll look like this because that's where we're changing our concavity. So the preview, you didn't know that, and that's okay. But our concavity is going to change where we had the max and the mins from our derivative graph. So little heads up there, we'll talk more about that later. But the purple graph is a potential of what it could possibly look like for the graph of f. So when I said we could have had it wiggling all the way up here in the first quadrant, you didn't have the extra information yet to know that it wouldn't really be that way. But we still don't know how high the purple would go or how low the purple would go. There's so many different possibilities, which is why we're sketching just a possible graph. Let's look at the position of an object if it's moving along a straight path. The position of an object moving along a straight path is given by this function. See the s of t right here? S is the position function. Find the formulas for velocity and acceleration. Velocity is the first derivative, and acceleration is the second derivative. So if we're looking for the velocity and we're looking for the acceleration, then that means that we're looking for the first and second derivatives. So let's try it. So that means that we're using our formula. So I'll write it up here. The limit as h approaches 0 of f of x plus h minus f of x all over h. So for this one, we have s instead of f, and we have t instead of x. So we need to adjust it. So that means that we're looking for our initial piece to be s of t plus h. So let's put it in. So that looks like 1.7 times t plus h squared minus 3.1 times t plus h plus 6.8. There we go. We need to clean this up a lot. Just like what we did before, we need to have our expansion here on t plus h squared. We need to FOIL that. So that'll look like t plus h times t plus h, which will give us t squared plus 2th plus h squared. So that'll be a FOIL. And then we need to multiply 1.7 by all that. So that will give us 1.7 t squared. And then 1.7 times 2 is going to give us 3.4 th and then 1.7 h squared. And then we need to distribute right here, minus 3.1 t minus 3.1 h plus 6.8. There we go. Now we need to figure out our s of t. So s of t from our original function is the 1.7 t squared minus 3.1 t plus 6.8. And now we need to put all this together so that we can put it into our limit function. So we have the limit as h approaches 0 of, start with our big top one right here, 1.7 t squared plus 3.4 th plus 1.7 h squared minus 3.1 t minus 3.1 h plus 6.8. Let me clean this h up right here because that was supposed to be a 1. Here we go. Now we need to do minus, and we need to do all of this. So let's distribute that negative through. Minus 1.7 t squared. Distributing our negative, a minus in front right here would be plus 3.1 t. Distributing our negative, a minus from the front, a positive here, minus 6.8, all over h. All right, I hope this cleans up a lot. Anything that does not have an h has to cancel. So here's 1.7 t squared minus 1.7 t squared. Okay, that canceled. 3.4 t h, we have an h. Plus 1.7 h squared, we have an h, we're okay. Minus 1.3 t plus 1, excuse me, switch that. Minus 3.1 t plus 3.1 t. Minus 3.1 h, we have an h, we're okay. Plus 6.8 minus 6.8. Let's write what we have left so that we can see it. So we have the limit as h approaches 0 of 3.4 th plus 1.7 h squared minus 3.1 h all over h. So we need to pull an h to the front, which means this one, the squared, and this one will all get factored to the front. We can cancel our h's, and now we can substitute in our 0 for our remaining h, which is just this one. So we will get the limit. Nope, no limit anymore. We're evaluating it. We don't write the limit. We will get 3.4 t plus, well, 1.7 times 0 will be 0, so that's gone. Minus 3.1. So our derivative, s prime of t, equals 3.4 t minus 3.1. And that's going to be the formula for the velocity. So this will be v of t, the velocity of t. Now we need the acceleration. So if we want to find the acceleration, we repeat this exact same process again. Acceleration is a of t, and that is the derivative of the velocity. So I'll let you do that part. It's very similar to the one that we just did in number 4, part A. I'll let you do that part, and I will tell you that it works out to be 3.4. Hopefully you're noticing a pattern with these derivatives. We'll see that pattern coming into play quite a bit in our next sections, but hopefully you're starting to notice a pattern. Number 6, the figure shows the graphs of 3 functions. One is the position function of a car, one is the velocity of the car, and one is its acceleration. Identify each curve and explain your choice. So remember, let's put these all together. So the first one is the position. And that is s of t. Then if we take the derivative of s of t, that gives us the velocity, which is v of t. And if we take the derivative of v of t, that gives us the acceleration, which is a of t. So the second derivative is also the second derivative of the position is also the first derivative of the velocity, which is also the acceleration. So made a little table here for you. So hopefully that helps you figure it out. So we need to figure out which one is which. So we have a position graph. We have a velocity graph. And we have an acceleration. And we have to figure out which graph over here, A, B, or C, goes to each one. So there's a couple things that I'm noticing. First, right away, when I look at these graphs, I'm noticing there's a few maximums. We got one right here. We got one right here. There's a minimum right here. I'm noticing right here, we have a spot where we're crossing the x-axis. So those are a few biggies that I'm noticing. So let's think about what we could do to identify different pieces of those. So when we look at a maximum or a minimum, that means that the derivative of that point is going to give us 0. So if I had a maximum in the original function, so in the position function, then that means that I'm going to get a 0 in the derivative. So that would be in the velocity. Does that make sense? Think about that for a second. If I have a maximum and I take its derivative, then that means I'm going to get a 0. Now let's look at this. Let's look at what we have. If A is a maximum and I'm going to take its derivative, then that means I would need a 0 right here, and I would need a 0 right here. I don't have that for either one. So it looks like I am not taking the derivative of the A function at all. Well, I only don't take the derivative of the acceleration. I take the derivative of velocity to get acceleration. I take the derivative of speed to get to velocity. But if I take the derivative of A, this graph right here, where I have the max and the min, I will get a 0. And I don't have that. So I'm going to guess that acceleration is A. Let's see if that works out. Let's see if we can figure out the others. If acceleration is A, that means I took the derivative of velocity to get to A. So how can we see some comparisons there? Well, here's B right here. I see that maximum still for B. So if I still have this maximum right here for B, and I take its derivative, I'll get 0. Look, that worked. So if I were to take the derivative of B, I would get the 0 that I'm showing on A. So if B is velocity and I take its derivative, I get that 0. We're okay. Process of elimination, that makes it look like C is our position function.